The next thing we're going to take a look at is NumPy, which is one of the many powerful and widely used data manipulation and analysis modules available for Python. NumPy provides the ndarray data type, which gives you very efficient and flexible n-dimensional arrays with highly efficient vectorized math functions, linear algebra capabilities, random number generators, and the like. Some of the other important and widely used modules that we'll take a look at include pandas for things like time series and spreadsheets, SciPy, stats models, which gives you a variety of statistical models, probability distributions, and the like. And we'll also see modules for plotting data, for scraping data from websites, and so on. Most widely used modules have a sort of standardized naming convention for module abbreviations. For example, the NumPy module is usually imported as NP, pandas is imported as PD, and so forth. For now, we're only going to worry about NumPy. And let's start taking a look at the NumPy ndarray data type. So we're going to import NumPy as NP, and we're going to compare and contrast NumPy's ndarray data type with the built-in list data type in Python. We know that we can create a list of a sequence of integers using the range function with the list constructor. Here, ls1 contains 0 through 4. The equivalent thing for NumPy is called an arange, the NumPy array-based equivalent of the range function. So np.arange builds a NumPy array whose data type is ndarray, which similarly contains the values 0 through 4. An important difference here is that items in an ndarray are guaranteed to be stored in contiguous memory locations, and access to the elements in an ndarray is much more efficient than access to the elements in a Python list. This efficient access comes with a price. An ndarray is not able to store arbitrary precision Python int values. Instead, an ndarray stores a more restrictive range of integer values, similar to the int values found in the C and C++ languages. Okay, so here we see that the type of ls1 is list, and the type of ls1 sub 0 is int. Let's confirm that. So the type of ls1 is list, and the type of ls1 sub 0 is going to be Python int, whereas the type of a1 is the NumPy module's ndarray data type, and the type of a1 sub 0 is something called an int32. So that means that it's a 32-bit wide integer value, and it turns out that the range of values you can store in an int32 is a little bit beyond plus and minus 2 billion. Not nearly the arbitrary precision range that we have with Python ints. An ndarray is iterable, so you can step through it using for loops. It's also very easy to convert back and forth between ndarrays and the various Python collection types. Okay, so here's my ndarray a1, and I can say for I in a1 do something. Just print I, let's say. I can easily create a list from a1, or a tuple from a1, or a set from a1, and so on. Okay, so V is a list, T is a tuple, S is a set, created from the items in A1. Not only can you use an ndarray to create these various built-in collection types, but you can go the other direction as well. You can use the various built-in collection types to create ndarrays. And here, rather than arange, you use the function array. So I'm saying A2 gets np.array, and then I can give any iterable that I wish. For example, here's a list, 3, 4, 5, 6. And whoops. And here is my A2 array. In this next example, I have a tuple of floats. I'm going to cheat and abbreviate. Okay, so here is my tuple contained between these parentheses, and now I'm going to create an ndarray of floating point values. Now, these are not Python floats. What they are, let me look at the type of the very first item in this array of 2 items. Okay, so A3 is an ndarray of 2 floating point items. Whoops, I accidentally looked at A2 sub 0. Let me look at the type of A3 sub 0. And what we see here is that this is a float 64 rather than a Python float. Now, it happens, actually, that a Python float is the same shape and the same pattern of bits as the NumPy float 64. So the range and magnitude of values that you can have in a Python float are identical to those that you can have in a float 64. In C or C++, there's a data type called double that would be the equivalent of the 64-bit floating point type. Now, we know that a list or a tuple or a set can have items of different data types. I can create a list containing an int and a float and a bool, and this is no problem. But it turns out that an ndarray, because of how it's implemented and because of the desire for efficiency, all of the items in an ndarray have to be the same data type. And so if you attempt to create an ndarray using mixed data types, here I have a list containing an int, and let me be clear, this is a Python int, a Python float, a Python int, and another Python float. NumPy is going to do something called upcasting to convert all of these values to the same data type, which in this case is going to be the float 64 data type within the NumPy module. All right, so here I'm saying A4 gets np.array, and then I have my list, Python int 3, Python float 4.5, Python int 5, Python float 6.7. But these are all going to get upcast to float 64 and therefore displayed as 3-point rather than integer 3 and 5-point rather than integer 5. I can check the type of one of these to make sure. A4 sub 2, let's say. All right, A4 sub 0, sub 1, sub 2, that's this guy, and its data type is, whoops, its data type is float 64. Sometimes this upcasting can result in surprises. For example, here I'm creating an ndarray from a tuple containing a float and a string, a str. Now, NumPy decides here that a string is a more complicated data type than a float, so it converts the float to a string so that everything in this array is represented as a string. So we have a string 3.14159 rather than the floating point value 3.14159. When I ask to see A5 here, not only do I see the values within the array, but the data type of these values is also reported to me. And this encoding here, the less than symbol U32, means that the items in this array are stored as Unicode 32-bit characters, character sequences. If I create an ndarray using a very wide mixture of types, here I have a Boolean, the special value none, and an int. Here, NumPy just sort of gives up and says, well, okay, fine. All of these are objects, and I'll just keep track of each one of them independently as some kind of object. And if I look at the types of the individual values in this array, I get told which type of object each one of these values is. We know that if we have a list object like ls1, that the star operator means to do repetition. So ls1 times gets 2 is going to give me 2 copies of ls1 appended together into a single list. If I say ls1 plus gets a single value, like 1, that's actually an error. Plus here means concatenation, but the thing on the right side of the plus gets operator has to be an iterable, not an individual int object. Right, so if I say ls1 plus ls1, let's say, this will give me the concatenation of 2 copies of ls1. For ndarrays, the star and the plus are treated mathematically rather than as concatenation and repetition. All right, so I have my array A1 containing these 4 int32 values. If I say A1 times gets 2, rather than getting 2 copies of that concatenated together, what I get is all of the items in A1 multiplied by 2. All right, so it started out containing 0, 1, 2, 3, 4, and now it contains 0, 2, 4, 6, 8. I can say A1 plus gets a scalar, and that has the effect of adding the scalar to each of the items within the array. So instead of 0, 2, 4, 6, 8, I now have 1, 3, 5, 7, 9. And if I add A1 plus A1, this gives me a vector sum rather than a concatenation. So the value of that thing is an ndarray containing 2, 6, 10, 14, 18. Okay, so star and plus and slash and minus are all treated as mathematical operators for ndarrays rather than star and plus being treated as repetition and concatenation. Now, an ndarray is a sequence. We can ask for a slice of an ndarray. That slice is always going to be a view on some underlying part of the ndarray. And let me show you some examples to describe what I mean by this. We're going to create A2 as an A range from 0 to 9. All right, and if I ask for A2 sub 2 colon 6, that means from sub 2 up through but not including sub 6. So that slice is going to be these values here, 2, 3, 4, 5. But it is not merely a shallow copy of those values as it would be for a list. It is an actual view, like a window on those 4 values. And consequently, if I say A2 sub 2 colon 6 gets a scalar, minus 8 in this case, what will happen here is that each one of those values, 2, 3, 4, 5, within A2 itself are going to be replaced with minus 8. Okay, so I have modified A2 by assigning -8 to each of the int32 values in that view. Similarly, if I were to say A3 gets A2 sub :3, all right, :3 means all the values up to but not including sub 3, so sub 0, sub 1, sub 2. But here again, this is not a shallow copy. A3 is a view on the first 3 items within A2. And so if I say A3 times gets 3, that's going to multiply each of those first 3 items by 3, and I'll see that reflected back in A2 itself. All right, so instead of 0, 1, -8, I now have 0, 3, -24 as the first 3 item values within A2. To get a copy, you must use the .copy method. So here I'm saying A4 gets A2 sub :5 .copy. All right, so :5 means 0 through and including 4, so I'll get these first 5 items from A2. But this time I will get a shallow copy of those, not a view on those. So here's A4. And if I say A4 times gets -1, that only changes A4. It does not change A2. Okay? So A4 is, because of the .copy method, an independent copy of part of A2. Okay, so far we have looked at one-dimensional ndarrays. Now we would like to take a look at more general n-dimensional ndarrays. One straightforward way of creating an n-dimensional array is to use the array construction function with a list of lists for a two-dimensional array, or a list of lists for a three-dimensional array. Similarly, you could use a tuple of tuples, or a tuple of tuples of tuples, and so forth. Here on slide 33, I'm creating a variable A1, which is going to refer to a two-dimensional ndarray, and I'm initializing that using a list of lists. So my first list is 1, 2, 3, 4. My second list is 6, 4, 2, 0. I've got a list of lists, and when I then display A1, the ndarray is displayed as this two-dimensional array. I can use the ndim attribute of an ndarray to find out how many dimensions the array has. Here, as I claimed, we have a two-dimensional array. And I can also find out the full shape of the ndarray by using the .shape attribute. Notice that ndim and shape are attributes, not methods that you have to call with parentheses. So we can see that A1's current shape is 2 by 4. That is, you can think of it as 2 rows and 4 columns. Another way of creating an n-dimensional array is to start out with a one-dimensional array of some kind and reshape the ndarray. So here I'm using arange to create a one-dimensional array of 0 through 11. A2 is my variable referring to that one-dimensional ndarray. And we can see that the number of dimensions of A2 is 1, and the shape of A2 is 12. Now the shape is always reported as a tuple. All right, so for A1 up here we got a tuple, 2 comma 4, indicating 2 rows, 4 columns. Here we're getting a 1 tuple because we only have 1 dimension, indicating that this ndarray A2 contains 12 items. Reshape allows me to make a copy of some existing ndarray in which the copy will have a different shape. Here I'm specifying 3 as the number of rows, 4 as the number of columns, and because A2 does contain 12 values, this reshaping will work. A3 now is a 3-row, 4-column copy of A2. A2 itself is not changed. A2 itself is still one-dimensional. Certain special shapes and kinds of arrays can be created directly with some construction functions shown here. For example, np.ones, if I create this as a 3 by 5 array, notice that my shape here is a tuple. So this is going to give me 3 rows and 5 columns of ones. Likewise, zeros behaves the same way, except for giving me zeros instead. All right, so here I have 2 rows and 5 columns of zeros. If I want an array, all of whose values are the same value, then I can use np.full. And I specify my shape, 5 by 5 in this case, and then my value, 3.14, let's say. And now I have a 5 by 5 array of the value 3.14. Either EYE, or identity can be used to create an identity matrix. So if I say np.I10, I have a 10 by 10 identity matrix, or np.identity, let's say 8, gives me an 8 by 8 identity matrix. So if you need an identity matrix of a certain size, you can use either one of those two functions equivalently. Now, you might have an ndarray that is quite large. For example, you might have 10 years worth of closing prices for a couple of thousand stocks. Roughly speaking, there are 250 trading days in each year. So if we have 10 years, that's going to be 2,500 days. We might have a row for each day, and then we might have a column of each stock. So this would be a 2,500 by 2,000 two-dimensional array of stock closing prices. It would be very common in a case like this to want to select only certain stocks and or only certain years out of this large data set, and we can use slices to do this kind of thing. So let's take a look at how we can use slices in two-dimensional ndarrays. First, let's see how to access an individual cell within a two-dimensional ndarray. We have this array A3, which has 3 rows and 4 columns. If this were a list of lists, we would be able to say something like A3 sub 1, let's say, to access the sub 1, that is the second row within this object, and in fact we can do that here. And then we can say A3 sub 1 sub 2, let's say, to access the sub 2 item within the one-dimensional array A3 sub 1, and that gives us the 6. But with an ndarray, we can go ahead and just use row, comma, column notation as we would in regular mathematics to access a particular cell within a matrix. So I can say A3 sub 1 comma 2 as a more familiar way of accessing this item 6 in row sub 1, column sub 2. A3 sub 0 comma 0 is the upper left value. A3 sub 2 comma 3 is the lower right value, the 11. Now let me create this 3 by 5 array that we're calling A1, shown here on slide 36. I'll go ahead and just hammer this in. Okay, so here's my list of 3 lists of 5 items from which I'm going to create the ndarray A1. A1 A1 is a two-dimensional. Whoops, sorry. A1 is a two-dimensional ndarray, and its shape is 3 by 5. Now let's suppose that I wanted to access just part of this two-dimensional array. For example, if I wanted to access these 6 items, the lower left part of A1, I can do that by saying A1 square bracket and then 1 colon, meaning as a slice that I want all of the rows in A1 starting from row sub 1 to the end. Okay, since there's only 3 rows in A1, this is going to give me row sub 1 and row sub 2. Then for the columns, if I say colon 3, that means columns sub 0, sub 1, and sub 2. Okay, so for rows sub 1 and sub 2, and for columns sub 0, sub 1, and sub 2, give me a view on just that part of A1. This is a view, so if I were then to say something like A sub 1 colon comma colon 3 times gets a minus 3, then all 6 of these items in the lower left part of A1 will have their values multiplied by minus 3. And the top row of A1 and the 4th and 5th columns of A1 are unaffected. Okay, so we've used slice notation to indicate which range of rows we want, and within those rows, which range of columns we want. Okay, so A1 is our 3-row, 5-column ndarray. A1 sub 2 is the row sub 2, that is the last row in the array A1. That is itself an ndarray, so I can ask for the shape of that ndarray, and I'm told this is a one-dimensional ndarray with 5 items, and in fact the number of dimensions is just 1. Okay, so if I say A1 sub 2 sub 1 gets 5, that basically means the same thing as saying A1 sub 2 comma 1 gets a 5, and we're going to end up putting a 5 right there. A sub 2 is the last row. A sub 2 sub 1 is the second item within that last row, and that's going to be changed to 5, as we see here. All right, now in slide 38, we're asking for a single row and all columns by using the slice notation. Recall that colon all by itself means from 0 up to but not including the length of the columns. So A1 sub 2 comma colon is really the same thing as A1 sub 2. It gives me all of the columns of that row sub 2. The shape of that indicates that there are 5 items in that row, and the number of dimensions of that row is just 1. It's a vector, it's not a two-dimensional matrix. But if I change the row 2 to the range of rows starting from row 2, so that now I'm asking for a slice of rows, even though row 2 is the last row in that array, my result is going to be a two-dimensional ndarray. Rather than being a one-dimensional ndarray containing 5 items, this is going to be a 1 by 5 two-dimensional array, as we can see by taking a look at the shape and the number of dimensions. Asking for A1 sub 2 colon is equivalent to asking for A1 sub 2 colon comma colon, that is all of the columns from all of the rows starting from row sub 2. Now, here on slide 40, we're specifying that we want all of the rows, but only some of the columns. So A1 subcolon means that we want to get a view on all of the rows, and then colon 2 means we only want to get the columns sub 0 and sub 1. This again is a two-dimensional ndarray with 3 rows and 2 columns, and ndim is 2. It's very important to keep track of the shape and dimensions of an ndarray, even when the ndarray only contains a single value. For example, here, again we have our array A, and if we ask for A1 sub 1, comma 2, A1 sub 1 is the second row, A1 sub 1 sub 2, comma 2 is going to be this minus 15. Now, that's a scalar. That's not an array. So that's a scalar value with no dimension. But if I ask for this range of rows from row 1 up to but not including row 2, even though there's only one row in that range, I get a slice rather than a row. And so when I ask for that slice and sub 2, I end up getting a one-dimensional array consisting of just the value minus 15. The same thing is true if I ask for row sub 1 and then columns sub 2 up to but not including sub 3. There again, I have a one-dimensional array containing the value minus 15. And then finally, if I ask for slices both in the row direction and in the column direction, but my resulting slice only has a single value in it, this is nevertheless a two-dimensional array. It's a 1-by-1 two-dimensional array. Okay, so I'm asking for A1 sub 1 colon 2, so row 1 up to but not including row 2. Then I'm asking for column 2 up to but not including column 3, so I'm getting just the single value 15, but treated as the single value within a 1-by-1 two-dimensional array. Okay, so this may seem a little bit picky and silly to be getting minus 15 as a scalar, minus 15 as a one-dimensional array in two different directions, row-wise and column-wise, and then minus 15 as a two-dimensional 1-by-1 array. But it is vitally important for you always to keep track of the dimensions of things and the types of things in order to know what attributes and what methods you can invoke on your objects. Failing to keep track of types and dimensions will result in getting lots of complaints about syntax errors from your Python environment. Now, again, let's imagine that we have this huge two-dimensional array where the rows of the array represent trading days and the columns represent different stocks, and what we have for each cell is the closing price for the given stocks on the given trading days. It may make sense to use slices to select ranges of trading dates, but it may not really make sense to use slices to select stocks that you're interested in. Perhaps the columns representing the stocks are organized alphabetically by ticker. You're probably not going to be interested in doing an analysis of all the stocks whose tickers start with an A. You would instead be interested in doing an analysis of tech stocks or pharmaceutical stocks or bank stocks or something like this. You can use what are called Boolean indexes to get more general row-by-row or column-by-column selections based on true or false values rather than just row ranges or column ranges. For example, here we have A1 again on slide 42, and I'm going to create a list named B rows containing true false, true. Okay, now I know that variable name looks like browse, but it's not browse. Trust me, it's b rows. And if I say a1 sub b rows, well, a1 sub something is going to be the row index of the row that I want, or the rows that I want. And if the index here is a list or some other sequence of Boolean values, then for each Boolean value of true, that will select a row. And for each Boolean value of false, that will not select a row. So the upshot is that I am selecting the sub-0 row and the sub-2 row. That is the first row and the last row, but not the middle row. And indeed, that is the result that I see. I have in this view of A1, this is a view, just as if I had done slices. In this view of A1, I have the first row and the last row, but not the middle row of A1. As I said, that is a view, so if I were to say A1 sub B rows times gets a -1, let's say, that is going to modify all of the items in the first row and the last row of A1 to be the negatives of what they were originally. So originally we had 0, 2, 4, 6, 8. Now we have 0, -2, -4, -6, -8. And similarly for the last row, we have the negatives of the original values when we looked at A1 up here. The middle row has not been affected. Okay, so that's how I can use a Boolean index to select certain rows and not others. Similarly, I can use my slice notation to say, all right, I want all of the rows, and then use a sequence of Boolean values. Here I'm manually typing in my list to indicate which columns I want. Okay, so in this notation, I want all rows. I'm using regular slice notation to indicate I want all rows, but I only want the first column, that is the sub-0 column, and the fourth, the sub-3 column. So I want to get this column, and I want to get this column, but not any of the other columns. And so this would be representative of selecting, let's say, Apple and Cisco, not Caterpillar, and not Bank of America or ExxonMobil. Okay, and so now I have all rows, but only 2 columns from each of those rows. Rather than manually determining ahead of time which rows I want to select or which columns I want to select with these true and false values, I can actually perform a Boolean test on every item within an ndarray by using the equality, inequality, and relational operators that we already know. So here's my A1 two-dimensional ndarray. If I ask A1 less than -5, this is going to give me back a Boolean ndarray of the same shape as A1. That is, it's going to be 3 rows and 5 columns. And for each item in A1, if that item is less than -5, I'm going to get a true. Otherwise, I'm going to get a false. So A1 sub-0 sub-0 is not less than -5, so I get a false. Likewise, A1 sub-0 sub-2 is not less than -5. But -6 and -8 are less than -5, so I'm going to get true for each of those items. And similarly, I'll get true for the -9 and the -15 in the second row, and for the -15 and the -9 in the third row. So I have 6 trues in the ndarray of Booleans that I get from that relational test. I can use that relational test directly as an index into A1. The effect here, when I say A1 sub A1 less than minus 5 gets 8 is that each of the items where the Boolean index is true is going to be changed from whatever its original value was to 8. And when I look at A1 now, I will see that I have 8s now in the first row where I used to have minus 6 and minus 8. I have 8s where I used to have minus 9 and minus 15 in the second row. And then 8s where I used to have minus 15 and minus 9 in the third row. So this works fine for individual equality, inequality, or relational tests. If you want to do some kind of logical combination of tests, that is, the value is less than 5 or the value is greater than 9, the value is even, and the value is greater than 20, you can combine these equality, inequality, and relational comparisons with the symbolic ampersand for and, vertical bar for or, caret symbol for exclusive or, and tilde for invert. Now, invert is a unary operator. It's not a binary operator. Basically, if you take true and invert it, you get false. Likewise, if you take false and invert it, you get true. Notice that these operator symbols have higher precedence than the equality, inequality, and relational operators, so you need to remember to use parentheses around them. This is annoying, but you'll get used to it if you do this a few times. Once again, I have A1. This time I've got 6 of the cells have been changed to 8. And if I ask for A1 greater than 5 and A1 less than 9, my idea here is to try to identify the items within this two-dimensional array that are between 6 and 8 inclusive. Okay, 6, 7, and 8 are the values that are greater than 5 and less than 9 when I'm dealing with integers. But unfortunately, I get yelled at here because the ampersand symbol has higher precedence than the greater than symbol or the less than symbol. So let me remember my parentheses and say A1 greater than 5 in parentheses and A1 less than 9 in parentheses. And now I will get a 3-row, 5-column Boolean index that will be true for each item that is strictly greater than 5 and less than 9, and false otherwise. All right, so now I have true for all the 8s. Okay, so here are the 6 8s that I had. I also have one more true here for this 7. Okay, so the 6 8s are all strictly greater than 5 and strictly less than 9, so I get true for those. And I also have this value 7 here in the sub 1, sub 3 slot, which is true. And so if I now say A1 sub, and I give this test here, I'm going to copy and paste, minus gets 5. Okay, so I'm subtracting 5 from all of these values that started out strictly greater than 5 and strictly less than 9. And what we'll see now is that my 8s have all turned into 3s. So I've got 6 8s that have turned into 3s, and I've got one 7 that has turned into a 2. Okay, so on slide 47, it's these red cells, which were the cells that were selected with true, that have been modified. The third style of indexing into an ndarray, in addition to slicing and Boolean indexes, is what is somewhat weirdly called fancy indexes. Fancy indexes was the original term for this. Nowadays, a lot of people call these integer indexes. Fancy is not a particularly descriptive term. Let's take a look at how these so-called fancy indexes work. And the first thing I'm going to do here is to set A1 back to the original 3x5 two-dimensional ndarray that we started all these examples with. Okay, so I've typed in A1 all over again, and now I'm back to the A1 that I started all these examples with. So for fancy indexing, within the square brackets, we specify in another set of square brackets which particular rows or columns we want. Now, inside the square brackets, the rows are the first dimension, and then the columns are the second dimension. So by using square brackets to index within A1, and then using square bracket 2 comma 0 as a fancy index, what I'm saying is that I want to get row sub 2 first, followed by row sub 0 afterward. So this not only allows me to select certain rows, but also to change the order of those rows in my result. And in fact, I can create duplicates of rows. I can say A1 sub 2, 2, 2, 2. And this is going to give me a result in which I have row sub 2 4 times, and that's all that I have. So I get an ndarray that has 4 copies of row sub 2 from A1. If I want to do fancy indexing on columns, I can select all rows using my slice, just colon, and then I can select the particular columns that I want to see and the order that I want to see those in. So A1 sub colon, comma, and then I want to see column sub 3, sub 2, sub 1, sub 2. All right, so column sub 3 is going to be the 6, the 7, the minus 2. I'm going to get that first, then column sub 2, 4, 5, minus 3, then column sub 1, 2, 3, minus 4, and then column sub 2 a second time. So my result here is a 3 by 4 array obtained from A1 using so-called fancy indexes. Okay, so if I say A1, and then I give integer indexes as my first dimension, let's say 3, 2, 1, and I give either nothing or a colon as my index 3. Oh, of course, index 3 is out of bounds. There is no row sub 3. Sorry about that. Okay, so A1 sub 2, 1, 0. Sorry, A1 sub 2, 1, 0. This is going to give me the rows of A1 in reverse order. All right, so A1 has 0, 2, 4, 6, 8 first, minus 5, minus 4, etc. last, and here I have swapped the orders of those rows. If I wish, I can use a colon for columns to explicitly indicate that I want all columns, but that's really the default, so nothing changes there. On the other hand, if I want selected columns from all rows, I do have to specify the colon to indicate that I want all rows, and then followed by my fancy index. Let me say 4, 3, 2 here. Okay, so I got columns. Well, now A1 has gone off the top of the page. Here we go. Okay, so now I've got columns sub 4, sub 3, and sub 2 in that order from all the rows. If you use fancy indexes for both the row subscript and the column subscript, somewhat strangely, that ends up creating a one-dimensional ndarray matching up these indexes pairwise. All right, so if I say A1 sub, and then sub rows 0, 1, 0, and 2, comma, and then sub column 0, 4, 2, and 0, notice that there have to be exactly as many row indexes as there are column indexes, and these things get matched up in pairs. So what I'm going to get is a one-dimensional ndarray containing item sub 0, 0, and item sub 1, 4, and then sub 0, 2, and finally sub 2, 0. So 0, 0 is going to be the 0. 1, 4 is going to be the 9. 0, 2 is going to be the 4. And 2, 0 is going to be the minus 5. And so I get 0, 9, 4, minus 5 in my one-dimensional resulting ndarray. Okay, so those are the three different mechanisms of selecting subsets of the rows and columns within a two-dimensional ndarray on which you want to do some kind of analysis. We have slices, we have Boolean indexes, and we have these so-called fancy or integer indexes. A couple of other very important facilities that NumPy provides are the random submodule, which provides a large number of pseudo-random number generators for many different probability distributions, as well as the ability to randomly shuffle values, permute values, and sample from values, and also the linear algebra facilities that NumPy provides. Random is a submodule within NP. If we say np.random.rand 2, 3, the rand function will generate pseudorandom numbers from a uniform distribution from 0 up to but not including 1. So these are float values in the half-open interval 0 up to but not including 1. 2, 3 here are the dimensions that I want this ndarray of random numbers to have. And here we see that I do get a 2-row by 3-column ndarray of pseudorandom numbers from the interval 0, 1. These pseudorandom numbers are full float 64 values with 16 digits after the decimal point, although by default, when you display an ndarray, it only shows 8 digits after the decimal point. Let me create this variable a1 to refer to a 2 by 3 ndarray of pseudorandom numbers from uniform 0, 1. Here's a1 displayed by default. If I say a1 sub 0, 0, that is an individual float 64 value, and I will see the full 16 digits of precision that Python displays for such a value. If you're not interested in that much precision, you can use the .round method to specify the number of digits that you want for the rounded values of the cells within an ndarray. Here I have a1. If I say a1 gets a1.round3, now I have values that have all been rounded to 3 digits. So whereas I used to have 0.9456 and so on, now I have 0.946 for my sub-0 item. All right, so rand gives me a pseudorandom number from uniform 0, 1. Rand n gives me pseudorandom numbers from normal 0, 1, that is a standard normal with a mean of 0 and a standard deviation of 1. This time I'm creating a 3-row and 5-column ndarray. If I stop there, each one of these pseudo-random values is stored out to 16 digits of precision, but perhaps I would rather have fewer digits of precision, so I could say something like .round3. Okay, so .rand gives me float values, float 64 values from uniform 0, 1. Rand n gives me pseudorandom values from a standard normal distribution. Rand int, on the other hand, gives me integer values from a uniform distribution where I have to specify the lowest value to be in this distribution and the value that's 1 too far. So if I say rand int and then 0, 10, the values that will generate are actually between 0 and 9 inclusive. And they'll be uniformly distributed among those values from 0 to 9. As the shape that I want this ndarray to have, I'm specifying 4 rows and 7 columns. Okay, so as I type that thing in, bear in mind that what I got when I wrote these notes is going to be different from what I get now. A couple of other useful facilities from the random submodule are shuffle, which enables you to shuffle the items within an existing ndarray, and permutation, which allows you to get a copy of an existing ndarray with the values in that array permuted. Now, shuffle does modify directly the ndarray that you apply it to, whereas permutation gives you back a permuted copy and does not modify the original array. So let's say I have A1 as np.arange 10. So A1 is now referring to an ndarray, one-dimensional, with values between 0 and 9. I'm going to make a copy of A1 named A2. When I display A2, I see that at this moment it's the same as A1. But if I now say np.random.shuffle A2, this does change the order of the items in A2. It does not change the order of the items in A1, though, because A2 is a copy of A1. If I say np.random.permutation of A1, this gives me back essentially a shuffled copy of A1 without changing A1. All right, so here is a permutation of A1, but A1 is unchanged. And each time I ask for a permutation, I get back another shuffled copy of A1 without A1 being changed. Given some collection of values stored in an ndarray, I can sample from that ndarray using the choice method. If I say np.random.choice A1, 5, this is going to give me back a sample of 5 items from A1 with replacement. That is, each time an item is sampled from A1, the next time I sample an item from A1, the probability is the same as it was before that I'll get the same value I just got. Hence, here in my test run that I just did, I get back 2 twice, because getting back a 2 does not in any way affect the probability of getting back a 2. And in this case, I happen to have gotten 2 back twice. When I wrote these notes, I happened to get 7 twice. You can request a sample without replacement by adding a keyword argument, replace equals false. And that will guarantee that each choice that's made is going to be distinct from the choices that have previously been made. So currently, altogether, NumPy's random submodule provides 35 different functions for generating pseudorandom numbers from a huge number of distributions. We looked at the standard normal distribution, which was rand_n. More generally, we can ask for np.random.normal, and we can specify the mean and the standard deviation and the number of items that we want to get as arguments. Okay, and here, of course, you can't tell for certain at a glance, but it certainly appears that the mean of all these values is going to be somewhere around 10, as opposed to somewhere around 0 or somewhere around 20. And again, looking at these values, it's sort of plausible that the standard deviation might be 2. It's probably not as low as 1. It's probably not as high as 3. And I can also have pseudorandom number generators from binomial distributions, exponential distributions, Poisson distributions, and many, many, many others. Linear algebra capabilities in NumPy are quite extensive. For example, if you have two matrices, A and B of appropriate dimensions, represented in ndarrays, then you can compute the product AB with the np dot function. Equivalently, you can specify A as the current ndarray object and use dot to multiply A by B. The transpose of a given ndarray is simply that array dot capital T. So np dot of A dot TA is how you compute A transpose A. For example, if I say A4 gets np dot random rand 1 3 round 3, I now have a vector of 3 random draws from a standard normal distribution. A4 dot capital T is the transpose of that. I can compute the inner product by saying np dot A4 comma A4 dot T, or the outer product by computing A4 dot T comma A4. The linalg submodule of NumPy provides many additional linear algebra functions and capabilities. Let's import numpy.linalg as LA. Notice that you can import a submodule using an abbreviation. And now I'm going to create A6 as a 3 by 3 matrix drawn from a standard normal. Okay, so here is my A6. One of the facilities that the linalg submodule provides is inverses, so I can say la.inv A6, and that will get me the inverse of A6, assuming that the inverse exists. And of course, we would expect that A6 dot its own inverse should give us back the identity matrix. Now, in fact, because of floating point round-off, we don't quite get the identity matrix, but we get something that's very, very close. The diagonal elements are, at least to the precision displayed, equal to 1, and the off-diagonal elements are very small. So if I round off all of these values to 15 places, then all of these very small values will be rounded down to 0. Whoops, in my example in the notes, rounding to 15 places did give us 1s on the diagonal and then 0s elsewhere. But here I've got one value that's still significantly different from 0, even rounded to 15 places. So let's try this again, rounding to 14 places. And this time we see that, yes, we do get a recognizable identity matrix. Now, since A6 is invertible, that implies that its determinant must be something other than 0. We can find out the determinant with the la.det method or function. All right, so the determinant of this matrix is 0.491 roughly. And in turn, if we try to solve an equation of the form ax equals b for some specific vector b, we know that we're going to get one unique solution. So let's create for ourselves this vector b. Let's create a vector just 1, 1, 1. And now I know that I can solve ax equals b, that is a6 x equals this vector b. The linealge submodule provides me a solve function that I can call, in which I give my matrix as the first argument and the right-hand side b as the second argument. And here we have our solution, that is the vector x. And of course, the value of x should be the same thing that I get if I multiply the inverse of a times b. So here I'm multiplying the inverse of a6 times b, and indeed I do get that value for x. NumPy has many, many other facilities as well. For example, it has a whole collection of vectorized mathematical operations that operate on entire arrays very efficiently. Square root, e to the x, log of x, etc. There are a bunch of statistical methods available in NumPy. We can also do sorting and set operations. We can also read from data files directly into ndarrays, or take an ndarray and put that into an output file in various formats. Okay, so that gets us to the conclusion of week 3. In this material, we discussed construction of the built-in collection types, namely list, tuple, set, and dict, by using the construction functions, that is list, open and close paren, tuple, open and close paren, set, open close paren, dict, open close paren, using iterables from which to construct these collection types. All right, so these construction functions use iterables. Now, a dict is a little bit trickier than a list, tuple, or set, because a dict requires an iterable on two tuples, or an iterable on pairs of values. And we saw a couple of tricks for doing that, namely the zip function that you can use to zip together two iterables into a single iterable on pairs, or enumerate that you can use to create an enumerated pair of values, where the first value is just an index, 0, 1, 2, 3, 4, and the second value, the corresponding value, is just a number or string or whatever it might be. We then looked at this more Pythonic approach for comprehending lists, sets, and dictionaries. Remember that a comprehension requires a for loop. If you've written some notation that creates a list or a tuple or a set or a dictionary, and that notation does not involve having a for loop embedded in it, then it's not a comprehension. So that is, for example, you can use a regular list construction with the list, open paren, and then an iterable and a close paren. That does indeed construct a list, but that is not a comprehension. I mention that because somebody might be picky about that in an interview, let's say. Okay, so for list comprehensions, you surround the notation in square brackets. For sets, you use curly braces. And for dictionaries, you can use curly braces, and you can either specify key colon value produced by your for loop. Your for loop in this case should be producing either one value or two values that can be used as the key and the value. Now, if you try to create a tuple comprehension, it doesn't actually work. What you end up getting is something called a generator. A generator is an iterable, and so you can give that as an argument to the tuple construction function, but technically speaking, that's not a comprehension. All right, we took a look at doing input and output in text files using the open function to open a file either for reading or writing. For reading, you can use a for loop on the open file because the open file is an iterable that you can step through line by line. For output, you can use this function called write, and in either case, whether you've opened a function for reading or for writing, you should be careful to close the file when you're done, so that if you later on need to access the contents of an input file again, you need to reopen the file so that you can step through the file again. And you can only reopen the file if you have closed the file. We took a look at the structure of function definitions. I'm not going to read through all of these details. I'm just going to point out that, remember, if you forget to have a return statement in a function, and that function is supposed to return a value, what you will get back from that function is none by default. Because each time you call a function, that function gets its own symbol table with its own copy of positional and keyword and local variables, you can write recursive functions. And the key things about a recursive function are you have to have a stopping condition that tells you when you've reached the conclusion of your recursion. Otherwise, you have to be able to split the problem down into discretely simpler parts. Hopefully, one of those parts will be so simple that you can just solve it directly. And then typically the harder part is in the same form as the original problem. And so you can call the function recursively with a slightly simpler instance of the hard part. Okay. And then finally, at the tail end here, we took a look at NumPy. We talked about the ndarray, n-dimensional array type, how to create them, how to access them. We talked about the idea that a slice within an ndarray is a view. So if you make modifications on a view, you're going to end up changing the original underlying ndarray. If you need to get a separate copy, remember the copy method. And we saw three different ways of accessing portions of an ndarray. We can either use slice notation with the colon, or Boolean indexing with true-false values, or finally, this goofily named so-called fancy indexing that allows you not only to select which rows and columns you want, but also to specify the order that you would like to get those things in. NumPy also provides random number generation and a large collection of linear algebra facilities, statistical facilities, sorting, etc. All right, so that was a lot of stuff, but that gets us to the end of week 3.